All right, so here's the plan for the course as a whole, sort of summarized again. We have logic, and then we have mathematics, or set theory, you could call it. And this is like the initial couple of weeks of the course where we study deduction and how to go in a valid way from one proposition to another and make deductions. And this is where we introduce axioms and then start proving theorems, where the propositions, rather than being, placeholders like these Greek letters, will become actual propositions, actual mathematical propositions. Now there are a lot of logical patterns that repeat themselves, and it would be nice to have those sort of codified into a set of rules. So those logical patterns of logical argument that repeat themselves, I'm referring to those as derived rules. So there are the rules of logic, things like modus ponens, that says if you have this and this, then you may deduce this. Those kinds of things are rules of logic. But then there are also derived rules, so more complicated rules that can be built up by following a pattern using the existing rules. So let's begin with derived rules. And let me write down the first one. Oh, and by the way, the reason we're looking at derived rules is not just to make the ideas available to you to use when you're making arguments, but also we're doing this to get practice writing. As we write out the sort of proofs for derived rules, or the arguments that derive the derived rules, we will have to make use of all the ways of writing things that we've been laying out, like proof by cases and proof by contradiction. So this will be a chance to practice writing before we start actually writing about anything in particular. All right, so here's our first derived rule that we're going to write a proof for. And this one, so each one has a title to help you remember it, or to help explain it, or to give you a chance to refer to it. This one is called Transitivity of Implication. So that's the title. And this is the statement of the rule. And you can see it contains a combination. The statement of the rule should be a proposition, kind of, or something like that, or something that tells you if you have these propositions, then you can get that one. If you look at it, it says if then, right? But it says it in two ways. First it says if then in words, but then it also has all these little if thens in symbols, there, and there. These implication symbols. So why this mixture of ways of saying things? So actually, this is the same. What's written here is the same as if I wrote this. Phi implies psi. And psi implies omega. All that implies phi implies omega. So the if then here is this implication, and the and here is this and here is a fully symbolic way of writing derived rule 7. So why don't we write it this way? Really, just because there are too many parentheses, it doesn't look pretty. So just to cut down on the number of parentheses, we use a mixture of the English words way of saying things and the mathematical symbols. So this just looks better. But remember that what we're proving in the end is an implication. So if we're going to prove derived rule 7, it's good to know that we are proving an implication. And if that's not clear to you without writing things symbolically, then write them symbolically. But hopefully it is somewhat clear when you read derived rule 7. It says if a bunch of junk, then a bunch of other junk. So it is an implication. So if I want to prove derived rule 7, or derive it, or establish the rule, then my task is to prove an implication. So what must I do? To prove an implication, I should assume the hypothesis and then attempt to prove the conclusion. So this kind of structure. If I want to prove if a bunch of junk, then a bunch of other junk, then I should assume the first junk, the hypothesis, and then come up with an argument convincing the reader of the conclusion. So here, I must start by saying, assume the hypothesis. The hypothesis is this junk here, also known as this here. So assume that phi implies psi, and psi implies omega. And now my task, my goal, is to prove the conclusion of the overall implication. So this, also known as this. So that's the goal. And, let me keep that. I don't really need to write down the goal in my proof, but let me do so just to help me proceed with the proof. So sometimes it helps. We must prove that phi implies omega. So sometimes it just helps to write down the goal. If you don't write it in your proof, sometimes writing it in your proof can also help the person who's reading your proof understand why you're taking the steps you're taking. But if you don't write your goal in the proof, then at least write it on some scratch paper. This rule is very simple, but when you're working on complicated theorems, often the goal becomes something very complicated, and it's hard to just keep track of everything in your head. So you want to write it down on scratch paper, at least. So we must prove this. So our goal then is to prove an implication. And we're in the same situation we were in before. So at the start of the proof, our goal was to prove this implication, right? This if-then here. And that led to the assumption here. And the goal here. Now, the goal is to prove this implication. This implication. And so we're going to assume this hypothesis and then attempt to prove this conclusion. So assume that phi, just phi, right? Now, what's the goal? I don't really need to write this in the proof, but I'm just helping clarify what I'm thinking as I'm writing the proof. We must prove that omega, right? Okay, so now I need to sort of look at the pieces that I have and see how I can use them to get to where I need to get. There's no other step where I can break things down. Everything's broken down sort of as much as possible. So all the pieces are in play, and now I have to execute some good plan. So what are the pieces that are in play? I know that phi implies omega. Oh, sorry, no I don't. I know that phi implies, let me circle the facts that I know are true. I know that phi implies psi, because I assumed it. I know that psi implies omega, because I assumed it. And I know that phi is true, because I assumed it. So these are the pieces that are in play. Somehow I have to use this to reach omega. Well, how do I use my pieces? Well, phi is really hard to use by itself, so let me focus on other things. These two implications. How do I use some implications? So let me go back here. And I know this is really simple, you're probably thinking, but I just want you to see how what I'm using is the rules that we have laid out and not just some stuff that I'm making up as I go. So to use an implication, if I have the hypothesis of the implication, then I can deduce the conclusion. So if I click on this, this is what I'm using, modus ponens. Given an implication and given the hypothesis, I can deduce the conclusion. So let's go back. So to use phi implies psi, I would need phi. Oh, but I have phi. That's great. So I can combine these two with a modus ponens and conclude psi. I don't know if that's helpful immediately maybe, but I'll just do it because I can. And if it's not helpful, I might erase it. So since phi implies psi, this thing, and phi, this thing, we have psi. Have means we know that it is true, or we may deduce it. Okay, so this is now one of the pieces that I've brought into play. This is now true. Well, I haven't used this implication yet, and modus ponens says if I know the hypothesis is true, then I can deduce the conclusion. And that's what I need, right? So it looks like we're finished. So another application of modus ponens. Since psi implies omega, and psi, we have omega. And we've now reached what we needed to reach, right? We reached this. So now I could put in a bunch of concluding sentences and kind of back out and state which implications I've proven. Like I could say, since we assumed phi and ended up deducing omega, we have now proven that phi implies omega. And then another sentence, since we assumed phi implies psi and psi implies omega, and we managed to prove phi implies omega, we may now conclude that all this giant implication. But I don't really need to write those concluding sentences. I can just put this symbol down that says that which was to be proven has been proven. This is good enough. And part of the reason it's good enough is that I was very clear about what needed to be done and why I was making these assumptions.